So here's another exam question. I'm gonna enter the lovely part on angular moment radiative transfer equations. So we're going to assume that the frequency integrated intensity I within an astrophysical object can be a function of height c and radiation angle mu equals the cosine of theta. That is not a function of time in this case. J, H, and K shall be the 0 first and second angular moments of I. And all of these are, of course, defined for you in the lecture notes. Hence, we can use some terminology in the question, as discussed. Start from the standard radiative transfer equation for I in a plane parallel medium. Assume the Eddington approximation K divided by J equals to 1/3 to be valid. Derive the following second order transfer equation for mean intensity J. 1/32J d tau 2 equals J minus S. Fixed vertical optical depth scale d tau. I put it to minus alpha dc here, and the source function S. Both are independent of the angle mu. Okay, so we have all our information. Let's see if we can do this. Can always do it. Yes, we can. All right. Frequency integrated first. Let's take it to do it the fun way. This would be the general, right? But we formulated it a little bit different, and we said that d dt is 0, yeah, and it's only variation in c, Cartesian, yeah. So then we of course know, and we know that cosine of theta here is mu, so then we can just write this out as mu di dc equals, and then we formulated this in terms of the source function, alpha S minus I. So here's our transport equation, yes? And we were asked to show that this is 4 is 1/3 d 2j d tau squared equals to j minus s. Okay. And here we were given that k, actually the cc component of k divided by a is 1/3. It's cc because that's the radiation pressure. Remember, in these type of situations, it's the same. So that's what we want to show. Okay, so then we wanted to define an optical depth scale, which we can define in the negative or in the positive direction. In the standard plane parallel, it's defined like this, right? We can do it in both ways. So we have this. We put it in the optical depth scale. Then it becomes the new d tau, and d tau is the fixed scale now, right? Equals 2 minus s plus I, or vice versa. And then we want to go here, okay? This is 1 in mean intensity J, right? We know the definition of J is 1 divided by 4 pi, solid angle integral d omega, which in this case, since we have a only variation in Z, it's just the phi angle comes out, right? Okay. We also know that we're going to have to use the other moments because it's sort of hinted to us in the exercise. So let's just pull those out as well. So the flux in the c direction, called the flux, the Eddington flux here, is just the equivalent, yeah, over mu. But then it's I mu, the mu. We know this. Remember the difference between the Eddington flux, which is the direct angular moments, and the physical flux F. Yeah? We go back and we realize this. This is often used in radiative transfer because it's, they're just angular moments higher and higher, so it becomes mathematically easier. You don't have to keep track of all the C's and, you know, the speed of lights and stuff like that, in the pressure and in the energy density. And then we had that the KCC component, called the radiation pressure, is just this mu, and then it's I mu squared d mu. Okay, so there we have them. Now we're going to get that, so we're going to have to, it's not a bad idea then to try to integrate this perhaps, and this is a fixed tau scale now. Remember, this is important because it's a fixed tau scale. It doesn't depend on mu, so we can take it outside integral. Yeah? So we can set that this is d tau, yeah? And then we're going to integrate the equation over the mu, okay? And perhaps we'll also take the 1/2 there, so we get it immediately, yes? So then we have d tau, we have taken this out, and then we have 1 integral over mu, and then we have the mu there, right? And the I there, okay? And then we have integrated this over the mu, okay? That is the left-hand side, and then we're going to have to do the same on the right-hand side, right? So that's minus s then. But we were also given that the source function was angle independent, that is isotropic. So we can just take that outside integral. So that is just going to be then s, and then the integral is just this over mu, right? However, for the second component here, the I, we're going to have to keep that in the integral. So that's going to be I then, and then d mu. All right. Oh, I didn't have to have. But then we can do identification of terms. This is h, right? So we have the h dc. This is just, well, this is from -1 to 1, right? So 2 comes out. So this is just minus s. And this is our definition of j. Okay, that's good. We have a first equation. Now, let's see. We need something. Oh, very clever, Jon. Well, anyways, we'll remember it. So now we have that, but we have, it involves h and it involves j, but our closure relation that we could assume was actually that k divided by j was 1/3, right? So we need to get to the k's. So then we need another integration probably. And that integration then is mu d mu. Now the way you realize these integrations is that these type of integrations were the ways that we derived the radiation energy and moment equations during the course by doing these type of integrations over angle. So we're going to integrate over that. Then we get d tau, 1/2. Then we have 2 mu's, I d mu equals to, on the other side, we're going to have s still isotropic, right, over mu d mu, plus 1/2 mu, then we had 1 mu and 1 mu. Okay, so what's going to happen here? Well, on the left-hand side there, we can identify this directly indeed as k, so that's the k d tau. On this side, interestingly enough, and here is where we have to realize that now the mu integral, as we know, go from -1 to 1. This is an uneven integral over our even interval. So how does this come out? We must have done this 50 times during the course, I hope. We know that it's 0, right? That's the point. And this is our definition of h, the Eddington flux. So that's nice. So now we have a second. Now we need to connect them. Well, here we can directly say we have that relation, right? So this we can also write as 1/3 dj d tau equals to h. As a side note, this is actually your diffusion flux approximation as well. You can work with that. That's the flux. That's the gradient in the energy density. Only now expressed as the mean density and in tau. Anywho, you have that, but we're still not there really because this involves the gradient, right? So we're going to have to take this, the gradient of this. But that's easy. That's just 1/3 the 2j d tau 2 equals the h d tau, but that is j minus s. Thus, 1/3 the 2j d tau 2 equals j minus s. Voila. Is that the same as we should? Yes, that is what we should show. So then we're there. This is sometimes actually called the diffusion equation. It's a little bit misleading because this is the diffusion approximation, and it's really just based on the Eddington approximation, which is better in general. But yeah, okay. Those are that. But I thought that since I like this, we're gonna work a little bit more with this. We're actually done with the exam question now, but we're gonna fill in some stuff just because we're having so much fun. I thought, remember what we did like last week when we discussed the issue of scattering and stuff? Then we saw that we could write, now we have this equation, right? 1/3, yeah? The 2j, the tau 2 equals j minus s. But it's sort of interesting to note that if we take our source function in this thermal plus scattering component, epsilon, remember your thermalization, plus b minus 1 epsilon j, right? That was there, where epsilon was our thermalization parameter, which essentially is then your alpha. If you take it, now we took the frequency integrated here, right? So this would be then alpha thermal plus alpha scattering. And you would really need to do this now frequency by frequency. But okay. If we just plug this into this equation, we see that what actually comes out is j plus epsilon b plus j, minus, right? Minus epsilon b, j minus epsilon b minus j plus epsilon j. So these cancel, and you're left with epsilon j minus b. So that's another way of saying that if you have a pure scattering situation, you actually get like a homogeneous equation. It's 0 on this side. And we discussed this in terms of that you don't really get a scale in your solutions here. The coupling in the energy, which this can be interpreted at, it's the mean intensity, so that's the energy density, right? The coupling between the energy and the matter comes through this thermalization, right? Which has to do with the epsilon and the Planck function B. Yeah. So that's why, for example, if you want to set this up in like a radiative equilibrium model or something else, then you have to care about what's the actual thermal component, because the scattering components always cancel. Put it another way, this is also why this iteration procedure that's discussed in the general transport equation is difficult in the case of scattering. Because in the case of scattering, then this is very, very low. And then when you try to solve the equation of transfer directly, it means that photons, they go through very large portions of the atmosphere before they interact. So you get a very non-local coupling there. But this actually offers, at least in the case of scattering plus a thermal component, this offers an interesting, attractive way of solving for the radiation field, and that is that, okay, what if we don't assume the Eddington approximation 1/3 here, but we put it into our general Eddington factor, F. Remember, we defined this. And then we solve this equation for the epsilon, yeah? And then, between each iterations, we try to then solve the transport equation only for the thermal part and update this. And then we can iterate on this. That's called the variable Eddington factor method, okay? Often used in radiative transfer solutions. And if you can formulate your source function in terms of a thermal and scattering component, that's actually very efficient, because then this can converge in terms of the Eddington factors fast. Side note. And then I wanted to do another thing on the same theme, which is sort of just seeing how these are expressions in different limits. Because now, what we're going to say, what did I say that I was going to do? I think I had at least like a setup for that. Okay, so we're going to consider again the frequency integrated radiative transfer equation, but time dependent now, and in the vacuum limit, again in 1D Cartesian, and then we're going to derive a wave equation for the energy density, and then we're going to see what generic Eddington factor, right? Here we have assumed that the Eddington factor is 1/3. What generic Eddington factor do we need in order to get the wave equation with the speed of light c, which is what we should do, right? Okay, so then we need to know, okay, what is our generic wave equation, right? Is d2u dt2 equals to some speed v, or is it the other way around? I need to check now. No, the t there. And then it's some speed v squared, d2u, where u is the variable, right? And if we have a one-dimensional along the c, which we're going to put this x2. That's the wave equation in the generic form, where v is the sound speed. So we want to take this wave equation for the speed of sound, speed of light, in the vacuum limit. We have 1/c, the I dt, plus, and now I'm going to put in the one-dimensional c directly, so it's mu, the I dc equals e to the minus alpha I, but that's just 0, because vacuum means this. Okay. So that's our equation. And now we're going to do the same thing as we did before. We're going to integrate first over angle omega, right? Now, if we integrate this over the omega, we get d dt, commute, 1/c, integral I d omega plus d dc mu, integral omega over mu I d omega, and just 0. But here we can identify this as dE, this is the energy density now, plus, and this is just the flux, the physical flux in the c direction, dc equals to 0. Okay. So there we have our number 1 now, in this case, and let's see what our number 2 gives. Just exactly the same as we did in the exam exercise, okay? Number 2 is just 2 times this, right? So that is then it is not 2, it's with the mu instead. Sorry about that. Yeah? And then it's 1/c, integral there. And then we have I mu the omega. Yeah. And then the second is going to be d dc. We don't have any c in there, but we have another mu, so it's going to be I mu squared the omega, and that's 0. And here again, we can do the identification. This is just the physical flux. So this will be 1 over c, the Fc dt, plus, and this is just our pressure in the cc direction, times c, plus c, the pressure cc dc equals to 0, or if we want, we can just divide through by this c, so that it's like that. So, like so, we have a second equation. Now we want to get this to a wave equation, so that, of course, involves a second derivative there, right? So it's likely going to be then a good idea to take the time derivative here, for example, and then we're going to use that they commute. So if we take the time derivative there, we see that this is 2 d2t plus, and this is d dc, and then the Fc dt, right? We take the time derivative, equals to 0. But the Fc dt we had here already, yes? So we can see, by just plugging this in, we move that over, we get a minus sign there, right? C squared comes up, and we move it over. We see that what we arrive with is d2e equals c squared d pcc d c squared. And now what generic Eddington factor do we need to assume for the wave speed to be the speed of light c? Well, it's not the equilibrium value. Actually, we need to assume that PCC equals to E, or that the Eddington factor is unity. Then the speed of light comes out. Well, the vacuum wave speed comes out as the speed of light, which it must come out. Otherwise, we don't have a consistent theory, right? So here, the answer to the question would be that we have to have an Eddington factor of unity. Now, it is interesting, and we mentioned this during the course, that if you plug in the equilibrium value here, you get a wave speed that is c divided by square root of 3, right? Because then it would be a 3 there, so the wave speed would be c divided by square root of 3, right? Now, and also as mentioned, in the early universe, this was the speed of sound. Because the adiabatic sound waves that were generated in the very early universe now, before the era of recombination, yeah? And that's actually causing this imprint and the fluctuations in the cosmic background, the overtones. They were damped by the radiation pressure, so they behaved like this. And they had a speed of light, a speed of sound that was c divided by square root of 3. Then when the era of recombination actually hit, then you lost your pressure support due to the photons. And then the speed of sound went from, or the radiative fluid went from being radiation dominated to gas dominated. And the speed of sound dropped like a rock to that of the gas temperature, which is, of course, that of the gas temperature is the speed of sound that we see here in our room, for example. And when it dropped like a rock, boof, that's when structure could start to grow in the universe. A discussion for the spring.